Welcome back to another episode of Heavy Wireless. This podcast is part of the Packet Pushers podcast network. My name is Keith Parsons, and today I have with me Luke Jenkins. Luke, how are you today?
Good. How are you doing today, Keith?
Great. A little while ago, I had the great opportunity to sit through a GPS GNSS course that you're teaching at WOPC, a little trial, and found it to be extremely interesting and thought it'd be a great topic for our audience. There are people who understand and enjoy wireless, and GPS is definitely a wireless thing, as is GNSS. So first, let's get at the very root of this. GPS, GNSS, what are they?
GNSS, Global Navigation Satellite System, is the generic term. Covers multiple different systems. GPS, which is the U.S. system, was the first one in wide use. Global Positioning System is what that stands for. So in addition to the U.S. system, when you hear somebody talk about GNSS, they're often talking also about the European Galileo system, the Russian GLONASS system, and the Chinese Baidu system.
Any other countries have their own?
Yeah, so those four are the worldwide systems that you can pick up just about anywhere in the world. There's some regional systems to augment those systems. Japan has one, QZSS, and I think there's a term for it or name for it in Japanese that I can never quite remember or pronounce quite right. And then, so that one benefits Japan, and then also because of where it is located in the world. I know a lot of Australian folks, and just basically if you're in that slice of the world, you can benefit from that. And then in the last few years, India has a new system that they've got up and running. INRSS, I want to say, is the acronym off the top of my head, but don't quote me on that one. But the Indian subcontinent in their neck of the woods, it's also only covers that part of the world kind of system, and it's not quite standalone, but I think they have designs of wanting to make it to where it could stand by itself without needing any of the other systems.
That sounds like there's a lot of satellites up there.
Yes, tons. We'll probably get into the history of GPS and global navigation systems, but just in the last, well, I guess it's been about 20 years now, but when I was first buying GPS units, you get one from Garmin from a Best Buy or Circuit City. It was like 12 or 24. The really high-end ones had 72 channels. So it's like, oh, you never need all those channels. But now, with all of the different satellites from all of the different constellations and the multiple bands, we'll get into that as well, I hope. It's up to like 1,400 signals is not unheard of. And the newest chips have, I want to say, just shy of 2,000 different channels that they can track.
Wow.
Yep.
That's way more than I remember the first one I had. If it got 10-meter resolution, I was really thrilled.
Yeah.
And I'm sure with more, and we'll talk more about how the resolution's changed. So let's go into the history there a little bit. I've read a couple of books on GPS and history, and if you haven't read them and you care, there's some good stories about how it came about. Can you give us just a little couple-minute intro of how GPS came about?
Yeah. So it was really kind of the aha moment was when some nice gentlemen from the Johns Hopkins University physics department, right after Sputnik launched, and they realized they could hear the Doppler shift as the satellite came up towards them. It was higher in pitch, and then it crested, and it's that whole locomotive coming past you effect that everybody knows about. So they realized that with that info, they could determine, based on how much Doppler shift there was, at what point in its orbit the satellite was at from relative to them. So you take that, and if you know where you're at, you know the orbit of the satellite, Doppler shift, you can solve for the current position of that satellite. But they were tasked the next year or so with flipping that. And if you knew where a bunch of satellites were, the Doppler shifts of them, their orbital mechanics, could you determine where you were on Earth? So solve for the opposite end of the equation there. There was need for even just general precision or few kilometer precision navigation for the system or the purpose in mind was actually submarine launched missiles. So the submarines would come up and they wouldn't know where they were. They needed to figure out where they were so they could program in where the missiles needed to go. And so that was good enough for that.
Well, thanks for that investment to solve one problem. We now have a solution that can help all of us. They actually did go through a phase right after that Sputnik event where the U.S. government had them build sites on the ground
Yes.
to see where satellites were. Kind of like we figured out where the satellites are by their Doppler shift. Can we get more precise? And they built a whole network of ground stations thinking that was going to be the answer. Eventually, we end up with satellites in the air, and they use time. So atomic clocks up there in those satellites. How do you end up using time to determine where you are?
The way that you solve for the equations in the modern age is the satellites say what time it is over and over and over, really quickly at a high cadence. And if you know what the basic modulation is and how the satellites work, then you can listen and figure out, even if you don't have any information about the current orbital state of the constellation, using time from each satellite, and then using a slower modulation they actually send out over about 10 minutes, the current status of the constellation, where the satellites should be. And then using that time, you're able to start determining with more and more accuracy how far away you are from each of the satellites, which you add up more and more satellites, and you're able to solve for where you are. I guess you need two of them to figure out where you are in the overlap of two circles or spheres. And then you need more satellites to then add additional points where those spheres intersect to get a very accurate location.
And some of those intersections are a couple miles of altitude, so you're probably not there.
Yep.
So it sounds like just a whole lot of math.
Yeah, really, really complex math that I don't understand, but I'm very glad that there are enough folks out there who are good enough with that.
And we just get to use them.
Yeah.
So most of the GPS stuff we use is a station that sits on the ground. It listens to these satellites. If you think of the time, if we know exactly when the time left and we know when we received it, that gives us a differential. The differential is in time, but we know it goes at the speed of light, so we divided the speed of light. And we can kind of think of, we have a string to each one of the satellites, and where in the world with this length of string from this many satellites will they intersect? And that's where we are.
Yep.
How do you get even higher resolution than that?
The easiest way, the biggest wins are you start solving for your location, and then you use that information to solve using a variable of swapping in and out one satellite at a time or one signal at a time, and you look for any that are just way off base. So we remove any that that just give us bad data, but then as you add more and more points where you overlap, you're able to get more and more precise. And then also there's 3 different bands that are used by most of the systems that each of those bands, the L1, L2, and L5, they correlate to L1 is about 1.5 gigahertz, and then L2, 1.2-ish off the top of my head, and then 1.1 is L5. Those different frequencies get different atmospheric effects, different ionosphere effects, different perturbances in the atmosphere. So if you have a satellite and it's sending out both an L1 and an L5 or an L2 or all 3, then you're able to eliminate the difference in the time as a measurement of distance if you're able to measure that across different frequencies which are impacted different.
And so it is impacted by weather or atmospheric or
space weather.
Sunspots?
Yeah, sunspots. It's the electromagnetic effects of the atmosphere. So you hear about, the ionosphere and tropospheric ducting and all these different effects that can that our atmosphere can have on radio waves, and that's true whether they're from the ground going to the ground or from space to Earth. And in the world of geolocation, that equates to uncertainty, usually just because of additional delay, depending on how electrically dense the atmosphere is, we'll say.
Well, if we know that there is some change in the atmosphere in one of those, it's pretty localized. I mean, from where we are.
Often, yeah. Yep. But the scale does vary. So if, like you mentioned, sunspots. So if you have a big solar storm event and just this giant coronal mass ejection of high energy particles comes and smacks the Earth's magnetosphere, and that could really mess things up for half of the planet, the half that's pointed towards the sun. But then there's other smaller, more localized effects. So I wouldn't say it would be, kilometer to kilometer in difference, but they, for example, the FAA, the Federal Aviation Administration, they provide correction data, and they have, I want to say it's about 30 different ground stations located at different major airports in different parts of the continental U.S., Canada, Mexico, Hawaii, and Alaska. And they have that many for redundancy, but also because the atmospheric effects from Salt Lake to Boise are going to be different.
Well, can we localize that?
Yes. Yep. So in addition to the FAA and their systems, there's many different systems around the world, across the U.S., lots in Europe, that can be base stations to use as reference points, where it is a well-determined, either via long periods of surveying in using GPS signals or GNSS signals, or some of them are actually surveyed using traditional, spotting type technologies for surveyors. And if you have a known location and you solve that same math for, well, I know I should be here, but the equations for using L1 GPS say that I'm actually 30 centimeters northwest. Let's correct that. Let's figure out what adjustments we need to make to each of the signals from the satellites and where they're at to bring that back into the most accurate location possible.
So we can add a terrestrial base station that's calculating those to give you that offset.
Yep. And then those offsets, 30 years ago, they were sent out via radio waves. If you were near an airport, you could tune and get corrections for your GPS via that. Surveyors, same thing, where you would pay into a system and they would give you the frequency to tune your UHF radio to and the keys to decrypt the corrections for the local surveyed in base station. Now everything's over IP in the world, including corrections, and so there's NTRIP, it's corrections over IP.
So kind of like an NTP server, only with GPS corrections.
Exactly. Yep.
Well, let's back up a little bit. And a lot of people have had experiences with GPS, handheld GPSs, and I'd like to talk about both the time it takes to find and lock your first time, and the second, and which leads more into what wireless guys would like to know, is how do we get GPS signals indoors? So let's tackle the first question. Why does it take a long time sometimes? Like my GPS just sits there, especially when I travel.
Yep. Yeah. So depending on what kind of GPS you're talking about, if it's a Garmin hiking GPS that's been sitting on your shelf since you last went hiking weeks or months ago, and you power that on, it does not have any memory. It doesn't have any. It doesn't have the almanac, is what they call it. It doesn't have any almanac data of which satellites are active, which codes they're using as their reference codes, gold codes, and where in space each of those satellites should be. That information is, the older it is, the less valuable it is, but you wouldn't usually use it if it was more than a week old. So if it's just a quick little turn off, turn on, you're hiking one day and then you're hiking the next, you turn back on your Garmin, it will probably lock pretty quick. But if it has 0 data saved, it has to listen for the full almanac to be sent out via the satellites. And that is additional information that's sent out on top of it's now 1235.00001 seconds. So it's a much lower bitrate, baud rate modulation on top of the time signals that you have to just be listening to the satellites and be listening long enough for them to give you the full set of information you need to be able to then know where the satellites will be, which ones are active, and then start solving for what time it is and where you're at.
Well, that leads into my next question. For Wi-Fi, especially 6 gigahertz, and we're looking at going to standard power, which requires an FCC approval, and FCC approval requires exactly where you are. Many vendors have now started to add GPS modules specifically in their outdoor APs for 6 gig, but also some indoors. I would think that the AP that's sitting and doesn't move could have basically all day long to hunt and find the GPS. So it would have an up-to-date almanac, but it's indoors. How do they still listen to satellites that are, way up in the sky?
The power levels, we talk about designing Wi-Fi to some level like negative 72 dBm or negative 67 dBm, some level in that neighborhood. If you look at the spec sheet for a GPS receiver, a GNSS module, down into the negative 140 to negative 150 dBm.
Like numbers, that's way below the noise floor.
Way below the noise floor. So you shouldn't be able to receive that, right? That's what we learned in high school physics or the first semester of physics in university. The trick is that if you have some hints on how to find the signal, you're able to dig it out of the noise, essentially. So each satellite, or there's a set number of gold codes, pseudo-random noise codes that are used for GPS signals, and they are the same. There's I think 32 of them for GPS, and so a receiver, when it first turns on, will start to listen for where those blips should be on the different frequencies for the L1 GPS band or whatever system it's listening for, and then it's able to essentially integrate or over a long enough period figure out decode all that data. So getting that signal inside, no matter how much you know about the signal, if there's just not enough signal coming through the walls or through the windows or through the roof, it's not going to work. I have plenty of buildings in my day job where they're modern buildings with LEED, gold, platinum, double diamond certifications, and they're made with the finest and low E glass and just solid foot of steel around every wall, I swear. And I just can't get a GPS signal in some of those
even at
buildings.
negative 140, it's still not happening.
Yeah, there's just not enough energy, from medium Earth orbit down to the GPS. So some of the approaches the different vendors have taken is external antennas, and you just have to tell the GPS how long of an antenna it has, and then it adds that to the uncertainty it uses. Or I think most vendors are using AP neighbor relationships. So if one AP, say an outdoor AP on the side of the building where it has great GPS lock, and going from AP to AP over 10, 20, 30 feet, you're able to get through really good RF insulation materials at those higher powers a lot easier than using GPS signals. So using RSSI or fine timing and measurement from 11 MC, or even something like ultra wideband, and it does kind of seem to be nobody's quite sure what exactly the FCC expects or wants. Every vendor that has AFC approval seems to have got just a little bit different approval, but it seems that the FCC is generally okay if you can trace a location back to an AP or a receiver of some sort that you know is a valid GPS lock, and you have a high degree of certainty between each hop or the hop or hops between APs. You add that additional uncertainty and just make the bubble of where the AP or the radio requesting an AFC grant, a standard power grant, is, and you hope that you have a low enough uncertainty and you're in an area that qualifies you to get a standard power approval.
So it sounds like if you're putting in 6 gigahertz outdoor and you want to use standard power, obviously your APs will have GPS, they'll have a lock, they make the request. So this process you described for taking an outdoor lock and bringing it to indoors, different vendors have different ways of figuring out where their APs are.
Mm-hmm.
And is the FCC having you add each of those uncertainties together before you request?
It's my understanding, yes, that it's as you solve the big GPS equations, the GNSS equations, and you have this number of satellites and their position in this place in their orbits in space, the GPS receiver says, I'm here with 3 meters of uncertainty or 30 meters of uncertainty, some amount, depending on the number of satellites and the number of bands and just the signal quality. And then, again, this is my understanding, but the general way that it seems to work these days is that each additional hop, you kind of determine if you're pretty certain that the hop is specific to that radio link. So if it's AP to AP and you've got a fine timing and measurement reading, you're able to just use that value. But say your 2 APs that are both connected to one switch, that would add 100 meters of Cat6 cable from the AP with a lock back to the switch. Even if it's shorter, the vendor I've looked at the most, they add 100 meters there. And then the second link from the switch to the other 6 gigahertz radio that's our AP that's trying to get an AFC grant, that's another 100 meters. So your 3 to 30 meter GPS lock now is 203 to 230 meters of uncertainty.
And since AFC cares about the Z-axis, 200 meters straight up puts you in line for all sorts of reasons why you shouldn't be broadcasting there. Not like your AP's actually sitting 600 feet in the air.
Right. Yeah. The incumbents that we're trying to protect with our use of 6 gigahertz, they're mostly point-to-point links or various things that are higher up. And so, yeah, it's if you're using the uncertainty of a LLDP or some similar link, the technology as it is today, the algorithms have been improved. They don't know whether it's flat across the ground and it's uncertainty in the X and Y, or if it is up a high rise or up a tower. And so they have to assume the worst case. And so your uncertainty is kind of this sphere of your location on the ground.
And obviously we'd like that bubble to be as small as possible.
Yes.
Well, you're teaching a 6-hour course on GNSS with toys they get to play with and build. What kind of things are they going to learn in your class?
Well, so I've kind of divided the class. It's 3 hours one day and then 3 hours the next. So I've kind of chosen that as a way to break it up. With the first day, I'm going to be teaching about GPS, GNSS, and how it works, and how to. It's kind of more focused on how to survey and find spots in your spaces that you're surveying. That if you're only installing GPS in certain areas, or you need to know where you can get GPS in a building or a structure, how to measure that using any sort of GPS unit or module that can get you that data. In the class, we'll be using a Quectel LG290P. It's a really cool new chip that can receive all of the bands and all the systems. I think it tops out at 1,400 signals at once.
That's all, just 1,400.
Yep. As I was prepping the units for the class with a good antenna, but still a mediocre one, inside my house, in my office, as the unit would power up, it would pretty reliably get a 1.3 meter accuracy within 5 minutes or less. So with that unit, or there's lots of other options for receivers that could be used for it. The idea would be, and we need to talk all of our Wi-Fi tooling vendors into doing this, but the idea would be that you would, as you're out surveying for wireless LAN, you would also be surveying GPS signals and recording those, not using the location to feed or to provide a location for your surveying. We'll talk about that. That's day 2. But just as you're indoors, where can you get any GPS signals at all?
And if you can,
how good?
Then upgrade that 6 gig AP to be one that has a GPS built in.
Exactly. Yeah. Or you will then know, even if it's a Wi-Fi 7 AP, a lot of the vendors are including a GPS in every unit of their mid and their better and best APs. So you don't have a choice of where you're going to put those GPSs, but it's still a question of, will you have enough APs in the locations you're putting them to get enough APs with GPS lock or GNSS lock to then provide a base location, an anchor location to their friends nearby.
And then day 2?
Day 2. The other thing that, I've been geeking out pretty hard on this for the last year or two. And the other cool thing that's happened in addition to just more signals and more satellites is that there's been technology for 20, almost 30 years now, to where if you have one of those reference stations and you're getting corrections, that you can feed it into variations of GPS and geolocation type algorithms to eliminate a lot of the uncertainty. In 2020, well, it's 2024, but 2025, the cost of chips to feed that correction data out and then also to directly ingest that data inside the chips, not needing any extra software outside, you can now build a pretty good base station to get centimeter level or at least decimeter level accuracy for under $200-$300, which is a huge drop from even 10 years ago when it was the very finest of the Trimbles and Lycia and all of these vendors of TopCon units that you couldn't buy off the shelf. You'd have to talk to a salesperson and they would help you select the right
level
licenses.
that surveyors use.
Yeah, exactly. But now it's within the grasp of, the geolocation nerd like myself, or hopefully we'll be teaching enough of the wireless LAN community how to do outdoor surveys and get really accurate enough location to trust for your outdoor surveys.
Yeah, because I've been doing outdoor GPS surveys with likes of Air Magnet and Ekahau for many years now, but usually they're only useful in things like open pit copper mines where you don't have a legitimate map. Mm-hmm. If you can see where you are on the ground and there's sidewalks and light poles and trees and crosswalk lines, you can just walk to those. But it'd be so much nicer if you could just go and let the GPS do it.
Yeah.
But sometimes using just Garmin's as the input, if you're 10 meters off, you're not anywhere close to where you want it to be.
Yep. You definitely, with that level of uncertainty, you're much better off clicking on pixels on an image of an aerial image. So
hopefully we'll get to a point where we can use GPS surveys for doing Wi-Fi surveying to be I don't have to click. I'll just let and I'll trust what the GPS is giving.
Yep. And it's even getting to the point now to where we're able to get enough accuracy that it would call into question the clicking skills of the surveyor, but also how accurate the imagery is. So if you take just, a screenshot off Google Earth or Google Maps, do you kind of know where it is and all that? But, it's the dream, if you will, that I have is that we're using geolocation technologies to record radio signal surveys, wireless LAN surveys, all these surveys, and we're actually properly geocoding them. And then we could start using the kinds of tools that surveyors have been using for a long time and engineers, so that the data can stand alone. And if you happen to lose the exact screenshot that you use to gather that data, it doesn't matter. It's not tied back to some screenshot from a map. It is actually as in reference to the WGS 84,
The actual where you are in the world.
where you are in the sphere that we live on.
Well, Luke, thanks for your time today. If someone wants to follow up, if they are a GNS nerd and want to get involved, how might they find you?
Well, it's kind of in flux with, the social media is kind of splintered right now, but I do have a blog that is woefully neglected at wifiluke.com, but I try and keep all of my social media accounts up to date on my GitHub account. It doesn't seem like the world of GitHub and the coding locations have gotten too splintered, and so if you go to github.com/Luke Jenkins, that links then to my other social media accounts.
Well, you've been listening to another episode of Heavy Wireless, part of the Packet Pushers Podcast Network. If you have any ideas for topics you'd like to hear or comments, please go to the Packet Pushers website and you can leave comments there. We look forward to talking with you on a future episode.